So we are continuing now with section 2.2, area of a triangle formula, applications of right and non-right angled trigonometry. Quite a hefty title for this section. So when we begin trigonometry, we start with right triangles, and in particular, we deal with SOHCAHTOA. There's two formulas for right triangles. The Pythagorean theorem relates the three sides, and SOHCAHTOA, sine, cosine, tangent, relate sides and angles. So you have those two formulas for right angle triangles. When you go to non-right angle triangles, like we had in section 2.1, then we have the law of sines, and we have the law of cosines. Now, the law of sines and the law of cosines were covered in section 2.1. So now that we finished section 2.1, we're moving on to section 2.2, which is applications of those four formulas. Again, Pythagorean theorem and SOHCAHTOA for right angle triangles, and the law of sines and the law of cosines for non-right angle triangles. And we're going to start with the formula for the area of a triangle. Now, you probably, hopefully, remember that you already have a formula for the area of a triangle. It's 1/2 base times height. So if you have a triangle, oh, that's a horrible triangle. Let's try it again. If you have a triangle, maybe a right triangle, maybe not a right triangle, and you have one side, let's call it the base, and then you have the length from the opposite vertex down to the base, called the height. And it's important to realize that this type of situation includes a triangle that might look like this, where the height is again down from the opposite vertex, but this time is outside the triangle. It still holds in that case. Either way, we have a formula for the area, 1/2 base times height. Why is the formula 1/2 base times height? Well, if you think about it, a triangle is half of a rectangle. If you would actually copy this part and copy that part, you see that a full rectangle is two triangles manipulated in such a way to form a rectangle, which is why it's 1/2 base times height. So why do we need a new formula? And the answer is because there are certain situations where we don't have the height. And this occurs in calculus. A certain type of problem that pops up in calculus, you have a triangle, and what you'll have is you'll have one side here, we'll call it A, and you'll have a side next to it, you'll call it B, and you will know angle, they like to use the hat symbols, so you have angle C hat, which is the angle that is sandwiched between the two sides. And a new formula for the area of a triangle is 1/2 side times the sine of the sandwiched angle, 1/2 AB sine C. Of course, maybe you don't call them AB and C hat, maybe you call them BC and A hat or something like that. So it doesn't make a difference how you call them, as long as you have, that's the AB, BCA, or AC, sine B hat, these are all the same thing. It's 1/2 side times the sine of the sandwiched angle. So which formula for area do you use? It depends on what you're given, and it depends on which one is easier to use for that problem. Of course, they're both going to give you the right answer in situations when you can use either one. So let's do the following example. You have, it says a farmer owns a triangular plot, triangle A, B, C. There's a picture here in the book, so it's labeled ABC, where the lengths are AB equals 120 meters, BC equals 240 meters, and B hat is equal to 130 degrees. And the question is, find the area of the plot to the nearest integer. So which formula for area will we use in this case? Will we use 1/2 base times height? Well, we don't have the height. Can we get the height? Sure, of course we can. But is there an easier formula to use? Well, we have two sides and the angle in between them. So the area is 1/2 first side, second side, sine of the angle between them. So 1/2 times 120 times 240 times sine of 130 degrees. And it says to the nearest integer. So this becomes 11,031. And what are the units? Well, we have meters. So this is area. So it's square meters. Another example. We have another triangle here. And this one's labeled A in the top right, B here, and C there. It says the area is 29.6 square centimeters. B hat is equal to 25 degrees. And BC is equal to 7 centimeters. It says find the length of side AB, which we will call lowercase c. Lowercase c is kind of hard to see, but as long as we know what we're talking about, that's fine. So do we want to use, so the question is what formula to use. We're not looking for the area here. So your instinct might not be to use the area formula. However, you are given the area. So your instinct should be to use some area formula, either 1/2 base times height or 1/2 side sandwiched sine angle. In this case, I think it's pretty clear, especially because it's in this section where we just learned this formula. Since we have one side, we want this side, and we have the sandwiched angle, that we can write 29.6 is 1/2 first side, currently unknown side, times the sine of the angle between them. So 29.6 times 2 divided by 7 divided by sine 25 degrees. And this gives us that lowercase c. And in this case, they do not tell us to round to anything, which is why we use as a general rule 3 sig figs, 20.0. And what are the units? We have centimeters, we have square centimeters. So the answer is centimeters. Another example. It says find the area of a parallelogram ABCD. Not a triangle, but a parallelogram. Okay, now those should be parallel. If you really look close, it doesn't quite look parallel, but you'll forgive my lack of artistic abilities. Here's A, B, C, and D. BC equals 7.4 centimeters. AB equals 12.3 centimeters. And B hat is equal to 39 degrees. And we want the area of the parallelogram. Well, we only have an area for a triangle. And that triangle is specifically two sides and the sandwiched angle between them. So the only triangle would be this one, triangle ABC. But hopefully you know your basic geometry. And you can even look at the picture and kind of see that the other half of the parallelogram is congruent. It's a perfect flipped copy. And even if you don't see that, hopefully you know about parallelograms, that opposite sides are congruent and opposite angles are congruent. which means this one's also 7.4 centimeters. This one's also 12.3 centimeters. This one's also 39 degrees. And therefore, the total area is twice of 1/2 first side, second side. Sine of the sandwiched angle. The 2 and the 1/2, of course, cancel. If I was doing this myself, I wouldn't even write it, but it's nice to see it. So 12.3 times 7.4 times sine of 39 degrees. And since we're not given sig figs, we will use 3, 57.3. And we're using centimeters and we want an area, so centimeters squared. Hopefully that is reasonable and somewhat obvious and immediate. Another example. A roof is in the shape of an isosceles triangle. So an isosceles triangle, triangle PRQ, element of PQR. Why would they say PRQ when they say, that's just weird. That's just wrong. That's just wrong. But anyways, it's in the shape of an isosceles triangle, PRQ, where PQ equals RQ. So here's PQ and RQ. P hat is 61 degrees, and PR is 12 centimeters. Find the area of triangle PRQ. Well, you have two options here. One, of course, is to use 1/2 base times height, and the other is to use 1/2 side times the sine of the sandwiched angle. Looking quickly at the book's answer, they use 1/2 side sine of the sandwiched angle because, of course, that is the section. But if I was doing this myself, instinctively, I would say, wait a second, I can just come on down here, make a right triangle, use SOHCAHTOA to get the height, and then just do 1/2 base times height. However, that's not what they do. So let's just do it the way they did, just to have a little practice with this particular technique. And the answer is, let's find the third side, or find one of the other two sides, in particular the left side, because that way we have side and sine of the sandwiched angle. Of course, if we get the right side, it's the same as the left side because it's isosceles. So how are we going to do that? Well, it's not a right triangle. So we have two options. We have the law of sines, or we have the law of cosines. To do the law of cosines, we need two sides and something else. We certainly do not have two sides and something else, because if we had two sides, we wouldn't need to do any of these laws because we'd have what we need. So the only other option is the law of sines. The law of sines, we need a side angle pair and something else. We don't have that either, unless we can discover it. So because it's isosceles, we know that the two sides are equal and the angles opposite them are also equal. So this is 61 degrees. Equal congruence, I'm using them interchangeably. Once we know these two are 61 plus 61 is 122, and the other one is 180. So 180 minus 122, that remains 58 degrees here. And now you see that we do have a side angle pair, and we want a side. So 12 over sine 58 degrees equals the unknown side, we'll just call it x, over sine of 61 degrees. Take out the calculator. 12 times sine 61 degrees divided by sine 58 degrees. And this gives us that x, the unknown side, is to 3 sig figs. Even though I'm going to write 3 sig figs, I'm still going to use every decimal on my calculator, but I'm going to write 12.4 centimeters, which means that the area is 1/2 first side, second side, sine of the angle in between. So again, using all those numbers, 1/2 times 12 times 12.375999204 times sine of 61 degrees gives me, to 3 sig figs, 64.9, and we're looking for an area, so square centimeters. Let's do a couple more examples. Find the area of a triangular vegetable garden whose sides are, so there's a picture here. We have A, B, and C, whose sides are AB equals 15 meters, AC equals 7 meters, and BC equals 12 meters. So we, of course, you could use either 1/2 base times height or 1/2 side sine of the sandwiched angle. Because this is using these more advanced trigonometry, we'll go with the second one, even if the first one may or may not be easier, much like the last problem. So we need an angle. Any angle will do. How are we going to get it? Well, to use the law of sines, we need a side angle pair and something else. We don't have any angles. But to use the law of cosines, we need two sides and something else, which we do. So it doesn't make a difference which angle we use. I'll just pick this one here, down here, a hat. So we have a squared equals b squared plus c squared minus 2ab cosine of angle a hat. So 144, that's 12 squared, minus 49, which is 7 squared, minus 225, which is 15 squared. So that gives us negative 130 is negative 2 times 7 times 15 times cosine of a hat. 2 times 7 times 15, that's 14 times 15. That's what, 210, I believe. Just check, yeah. So this becomes negative 130 equals negative 210 cosine a hat. 130 divided by 210, or negatives cancel. So I get approximately 0.619 equals cosine of a hat. How do I get to a hat knowing cosine of a hat? I can do the inverse cosine, the arc cosine, because it's in the first quadrant. It's an angle that's less than 90 degrees. So I know that my calculator will give me the correct answer, which to 3 sig figs is 51.8 degrees. Once I know that angle is 51.8 degrees, now the area is 1/2 side sine of the sandwiched angle. So sine of the answer, again, use all the decimals, times 7 times 15 times 1/2 gives me an area of 41.2, and I'm in meters, so square meters. Oh, the book says cubic meters. How nice, another mistake. Okay, and then we have another example here. This is the last example before the next collection of exercises. This is a nice one. This is a good one. It says the floor of a gazebo has a shape of a regular octagon. We all have seen octagons. The traditional one is the stop sign, 1, 2, 3, 4, 5, 6, 7, 8. That's a horrible octagon. Let's see, will the computer, no, too slow. 1, 2, 3, 4, 5, 6, 7, 8. Well, it's better than my first one, so I'll keep it. But it's a regular octagon. So a regular octagon, that's horrible. I gotta do it again. Okay, 1 second. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, it is what it is. But a regular octagon is not just 8-sided. A regular octagon means all sides and all angles are the same. So use your imagination a little bit. It has a shape of a regular octagon with side length 1.2 meters. And is made of 8 congruent triangles. First triangle, second triangle, third triangle, fourth triangle, fifth triangle, sixth triangle, seventh and eighth triangles. Find the area of the floor. Okay, well, we have formulas for the area of a triangle, and there's 8 congruent triangles. So it's just going to be 8 times the area of any one of those triangles. So I'm going to draw a second one, which is just one of those triangles. And what's the area of one of those triangles? It's 1/2 side times the sine of the included angle. Now, because it's congruent, because it's all the triangles are congruent, we know it's isosceles. We know those two are the same, but we don't know what they are. It seems like we don't have a lot of information, but there actually is a nice feature, which is if I make a full circle here in the center, that full circle is 360 degrees. And it's divided up into 8 triangles, which means this part right here, the one that we're looking for, is just one of those 8 triangles. So it's 1/8 of 360 degrees. What is 1/8 of 360? It's just 360 divided by 8, which is 180 divided by 4, 90 divided by 2. What? That's 45, right? Don't want to do anything stupid. So 45 degrees. So we know that this angle here is 45 degrees. Now we have a side angle pair, but we're missing something else. Aha, but wait. The 3 angles have to add to 180. So 180 minus 45 leads 135, which is split evenly into 67.5 degrees here and 67.5 degrees there. Only need one of them, of course, to use the law of sines. I'm going to, well, first, now this is 45 degrees. Assuming we use that one, I'm going to take this and lower it a little bit because I do need to use the law of sines now to find one of those sides. So 1.2 divided by sine of 45 degrees equals a currently unknown x divided by sine of 67.5 degrees. So sine of 67.5 degrees times 1.2 divided by sine of 45 degrees. This tells me that x, the unknown side, is approximately 1.57 meters. And that's going to be my 1.57 and 1.57 because I'm going to use it for those 2 sides. So I'm going to square the whole decimal, multiply it by sine of 45 degrees. 8 and 1/2 is 4, so times 4. And this gives me an area to 3 sig figs of 6.95 square meters. And that takes us to exercise 2C. And there's 6 questions here, and then we go on to a little more, and then we do exercise 2D, which will have 5 questions. Again, as always, you should be pausing every time I pose a question and try to do it yourself. It's the best way to learn. So question 1, and I was just kidding when I said 6 questions because the first 2 have 3 parts and the third one has 2 parts. They like to trick you. So we have a triangle here. Here's the picture, something like this. And this is 28 centimeters. This is 16 centimeters. And there's an angle in between of 23 degrees, and it says find the area. So pause. Okay, well, this one is immediate, or should be immediate if you follow the chapter at all, because we have 2 sides in the sandwiched angle. So 1/2 times 28 times 16 times sine of 23 degrees gives me to 3 sig figs 87.5 square centimeters. B, another triangle. This one's shaped differently. This one is 7.25 centimeters. This one is 11 centimeters. And we have an angle in between 56 degrees. Pause. So this one's exactly the same. I mean, the numbers are different, but the approach is exactly the same. 1/2 times 7.25 times 11 times the sine of 56 degrees gives us to 3 sig figs 33.1 square centimeters. And then part C, another triangle. This one's shaped very differently. This one is 35 degrees down here. This side here is 10 centimeters. This one is 67 degrees. And wow, 7 plus 3 root 5 centimeters. Okay, who came up with that one? I don't know. All right, pause, find the area. So this one has one extra step because we have two sides. We just need the angle in between. How do I find the angle in between? Well, I have the other two angles. I have to add to 180. So if I do 180 and I subtract 67 and I also subtract 35, that leaves me 78 degrees right here. And once I know that, 0.5 times 10 times parentheses 7 plus 3 square root 5 end parentheses, because it's one object, times sine of 78 degrees gives me 67.0 square centimeters. So that is question number 1. Question number 2. Find the area of each of the following triangles. There's 3 triangles again. This time they don't draw me pictures, they just label them. This is part A. So side A is 13.6 centimeters. Side B is 9.2 centimeters. And C hat is 49 degrees. Go ahead, pause as usual. So I'm not even going to draw it because I know that C hat is sandwiched between A and B. So it's 1/2 times 13.6 times 9.2 times sine of 49 degrees gives me 47.2 units or centimeters, so square centimeters. B, side C is 19 meters. A hat is 33 degrees. B hat is 42.5 degrees. So go ahead, please, and solve this. So this one I am going to draw a triangle because it's more than one step and I don't want to do anything really silly. Side A, side B, side C. So A hat is down here. B hat is up here. I'm going to write that again, make it a little clearer, 42.5 degrees. And C, I'll erase and just put 19 meters. Well, even before I worry about whether I need it to find it, if I have 2 angles of the triangle, I can subtract their sum from 180, and that gives me the third side. Do I need it? Yes, because if I want to use the law of sines to find one of the other 2 sides, I need a side angle pair. I now have one. So let's say A over sine of 33 degrees equals 19 over sine of 104.5 degrees. And then solve for A. So 19 times sine 33 divided by sine of 104.5. This gives me that A is equal to 10.7 meters. Again, writing 3 sig figs, but keeping everything on my calculator. And therefore, the area is 1/2 side-side sandwiched angle. So I'll use A, which is 10.7. I'll use C, which is 19. And then sine of the angle sandwiched in between them. So I already have the 10.68859.876 in my calculator. So times 19 times 0.5 times 1/2 divided by 2. Either way, anything works. Times sine of 42.5 degrees. And that gives me an area to 3 sig figs of 68.6 square meters. Okay, and then we have C, part C. Side A is 25 centimeters. Side B is 14 root 2 centimeters. And side C is root 59 centimeters. As always, go ahead, try to solve this yourself. So I'm going to draw a triangle again because it's more than one step. And A, 25 centimeters, B, 14 root 2 centimeters, C, root 59 centimeters. I need an angle. I have all 3 sides. This is a fight for, not fights, this is a job for the law of cosines. Doesn't make a difference which angle. I'll just get this one down here. So that means that the side opposite, 14 root 2 squared equals 25 squared plus root 59 squared minus 25 root 59 times cosine of the angle in between them. That's b hat, because b is 14 root 2. So 14 root 2, well, 14 squared is 196, and 196 times 2 is 392, equals 625 plus 59 minus 50 root 59 cosine b hat. 392 minus 625 minus 59 gives us negative 292 is negative 50 root 59 cosine b hat. Divide by negative 50. Divide by the square root of 59. And I get 0.760 equals cosine of b hat. And therefore b hat is equal to the inverse cosine of that answer. I hit cosine. No wonder that answer made no sense. Cosine inverse of that answer, which is 40.5 degrees. So now I have this one, 40.5 degrees. Now that I have that one, I have two sides of the angle in between them. So the area is 1/2 25 root 59 sine of 40.5 degrees. Of course, I don't just have 40.5, I have 40.509061884. I use the whole thing, sine of the whole thing, times 25 times the square root of 59 times 1/2. And that gives me the 3 6 figs, 62.4 centimeters squared. Okay, that's question number 2. Moving on to question number 3. A gardener leaves a triangular plot of his garden for a plant nursery. Oh, sweet. The two sides of the triangular plot are, and there's a little picture here, are, well, that's not the same, but doesn't really make a difference, 23.5 meters and 15 meters. And labeled as A, C, and D. Who needs B anyways? Let's just skip it. So AC is 23.5 meters and AD is 15 meters. Part A. If DC is equal to 29 meters, I don't want to label it because this is only part A and part B might not have this. So I'm going to write if DC equals 29 meters. Find the area of the plot designated for the plant nursery. In other words, find the area of the triangle. So go ahead and do your thing. Solve, pause, you know the drill. Okay, so we don't have any angles. We have all three sides. I'll put it here for now, but I might have to delete it for part B. We have all three sides. So how do I get the third angle? I know this is a job for the law of cosines. Which angle do I want? Don't really care, but let's go for this angle here. So let's see what we got. 23.5 squared, because it's got to be the one opposite, equals 15 squared plus 29 squared minus 2, 15, 29 cosine of d hat. So 23.5 squared minus 15 squared minus 29 squared divided by negative 2 divided by 15 divided by 29, I get 0.591 equals cosine d hat. So the inverse cosine of that gives me that d hat is equal to 53.8 degrees to 3 sig figs. Now that I have it, therefore, the area is 1/2 side, sine of the sandwiched angle. So sine of this entire decimal times 15 times 29 times 0.5 or times 1/2. And I get 176. And we are in meters, so square meters. So that's part A. What does part B say? 0.5 kilograms of herb. Side with an H. 0.5 kilograms of herb seeds will cover an area of 150 square meters. Determine the mass of seeds in kilograms needed to plant the plot with herbs. Well, we have 176 square meters. And again, I'm using 175.5279425. I'm using all the whole decimal. And what we're going to do here is we're going to multiply by a correspondence, which gets rid of the meter squared in the denominator and introduces the unit that I'm looking for in the numerator. And we have the correspondence that 0.5 of those corresponds to 150 of those. So if I take 175.5279425 and I multiply it by 0.5 and I divide it by 150, I get to 3 sig figs 0.585. And my new units are kilograms. All right, that is question number 3. I haven't done purple yet. Question number 4. Find the area of the parallelogram ABCD. So here's a parallelogram. Wow, okay. A, B, C, D. With BC equals 7.4 centimeters. BAC angle, BAC, so I have to introduce this right across. And BAC angle is this one down here, 44.5 degrees. And ACB angle equals 91 degrees. And they want the area of the entire parallelogram. So pause, and now welcome back. So we need a second side. Specifically, AB would be the most convenient to use, and we can get it immediately from the law of sines. If I call this side C, C over sine of 91 degrees equals 7.4 over sine of 44.5 degrees. So 7.4 times sine of 91 degrees divided by sine of 44.5 degrees. This tells us that the third side C to 3 sig figs is 10.6 centimeters. And therefore the area is 1/2 of twice, or it's twice 1/2 AB sine C, or 1/2. It's the formula for a triangle times 2, because it's a full parallelogram. So the 2 and the 1/2 cancel, and I'm just left with 7.4 times 10.6 times. Oh, and we need one more thing. We need the angle that's between them. We need B hat. That's not a problem because we have 91 and 44.5. So 180 minus the sum gives us 44.5 degrees for B hat. So sine of 44.5 degrees times the entire 10.55610.665 times 7.4 gives me an area in centimeters squared of 54.8 square centimeters. Okay, question number 5. A regular hexagon is inscribed in a circle. Ooh, so this is going to be a fun thing to draw. So we have a circle. That part was easy. And now we want a regular hexagon. So 1, 2, 3, 4, 5, 6. Okay. I didn't try to draw a 6-sided hexagon because there's no way of knowing where it would have landed. But the radius of the circle is 9 centimeters. So 9 centimeters. And they call this L. They give it a name. Oh, they give everything a name. Let's see. We have A, B, C, and then what the hell? Let's go to I, J, and K. Why not? A, B, C, I, J, K now. Okay. It says find the area of the hexagon. Pause. Welcome back. So we just did a problem like this. It's a regular hexagon, so that means all I need to do is find the area of one of the triangles, and because they're all congruent, all 6 of them are equal. So the area is 6 times any one of them, which is going to be 1/2 times side, sine of the angle in between. Well, notice that this is 9 centimeters, and so is this, because it's also a radius, which means if I use those two sides, they're both sines. They're both 9s. And now I just need the angle in between. Well, using the same trick as last time, if I go all the way around, that's 360 degrees. Last time was an octagon, so I divided it by 8. This is a hexagon, so I divided by 6. That's a 60-degree angle. So now that I know this here is 60 degrees, and these are both 9 centimeters, I can just do 1/2 99 sine 60 degrees and multiply it by 6, and that gives me the area of the hexagon. So 9 times 9 is 81, 6 times 1/2 is times 3, times sine 60 degrees, which is √3/2, and this gives me an area to 3 sig figs of 210 square centimeters. Of course, if I find the area of the entire circle, we know that formula is pi r squared, so 81 times pi is 254, which of course is bigger, which means not only do I know the area of the hexagon, but if the question was a little bit deeper, it asked for the area of the portion of the hexagon, a portion of the circle that's not part of the hexagon, I'll shade it, this part here, then I now know how to do that, because all you got to do is find the area of the hexagon, find the area of the whole circle, and do bigger minus smaller, and you get the part that's in the margins. Standard technique for finding an area. Find this, take that away, and you're left with what you're looking for. And finally, question 6. A garden is shaped in the form of a regular heptagon, MNSRQPO, and they draw it here, but 1 second. And then they have a circle with center T and radius 25 meters circumscribes the heptagon as shown in the diagram below. So I'm going to first start with the heptagon, with the circle. And then we have 1, 2, 3, 4, 5, 6, 7. Within the limits of my artistic abilities. And we have O, P, here's M, N, S, R, Q, and there's point T in the center. Okay. And the radius is 25 meters. Because the radius is 25 meters, I can just take this to any point here. For example, here's a radius of 25 meters. The area of triangle MSQ, so I'm going to erase that for a second, only because it might get in the way. So MSQ, that's M to S to Q. The area of, triangle MSQ is left for a children's playground, and the rest of the garden is planted with flowers. Okay, so where were we? Okay, so the area of triangle MSQ is left for the playground. I'll draw a little person in here so we remember this is for the playground. And the rest of it is for flowers. And it says, find the area of the garden planted with flowers. So this is basically, well, first, as always, pause and try to do it yourself. Okay, so this is exactly what I just said, right? If you want the area of the portion of flowers, you take the whole circle, which is the area of the entire circle is pi times the radius, which was given as 25 squared, 625 pi, with the appropriate units, meters squared here. And then we're going to take the area of the playground, which we have to find. And when we subtract them, that gives us the area of the flowers, which is what we're looking for. So we're not going to directly find the area of the flowers, but instead we're going to find the area of the playground, which is basically the area of this red triangle. Okay, so how are we going to do that? It's a triangle. So it's either 1/2 base times height or 1/2 AB sine C. And that's most likely going to be the one that we use here because, of course, it is in this section. And we have nothing right now. We have nothing. We know that the radius of the circle is 25 meters, but we're not actually using that because T, as you can see in the picture there or in my picture, is not actually on any of the sides of this triangle. So we got to do it in a more sophisticated way. So how are we going to do it? Well, first notice that it's isosceles because since it's a regular heptagon, that means that M to S, which is a jump of 2 vertices, M and S are Q, it's symmetric. There's a certain symmetry here where there's no difference between one versus the other because everything is perfectly arranged in a regular pattern. So we know that we have an isosceles triangle. That's one thing, which is probably going to be very useful. Let's see what else we have here. Well, we know that there's 1, 2, 3, 4, 5. There's 7. It's a heptagon. There's 7 corners of this thing. So the question then becomes, what is this angle here? So for this one, we have a formula which I don't think I saw in the formula sheets, but it's a good formula to know. So you know that a circle has 180 degrees, sorry, not a circle, a triangle has 180 degrees amongst its 3 angles, right? A triangle, the 3 angles at 180 degrees. What if it's a 4-sided figure? Well, for a 4-sided figure, you can basically make 2 triangles, 1, 2, 3, and 4, and 5, and 6, and that adds to 360 degrees. And if it's a 1, 2, 3, 4, 5, you can make 3 triangles. And here, if you add up all the angles of the 3 triangles, getting all the angles there, that's basically 3 triangles. It's 540 degrees. In general, you take the number of sides, you subtract 2 and multiply it by 180 degrees. And this gives you the total angles. Notice how it works for 3 sides, for 4 sides, and for 5 sides. 3 minus 2, 1 times 180, that worked. 4 minus 2 is 2 times 180, that worked. 5 minus 2 is 3 times 180, that worked. In general, here we have 7 sides. 7 minus 2 is 5. 5 times 180 degrees is 900 degrees. And those 900 degrees have to be distributed amongst the 7 different corners, 7 vertices. But by symmetry, they're all the same. So 900 divided by 7 gives us, to 3 sig figs, 129 degrees. Now that I know that's 129 degrees, I can do 180 minus that. Not sure if I need this or not, but just to have, and this tells me that my other 2 angles are 25.7 degrees. So that gives me those 3. I might not have needed them. We'll see. I haven't gotten that far in my thought process yet. But we now at least have the 3 angles of the triangle. Now, 3 angles of a triangle are not enough to do anything because you can always just enlarge the triangle and essentially you have the same 3 angles, so the sides can really be anything. So there has to be something more here that we can do. And so the answer is, we know it's isosceles. How can we use this information to find the, one of the sides of this triangle? So here's what we can do. I'm going to need a different color here. And the only length we have is the radius. So what I'm going to do is I'm going to shoot out a radius here. And I'm going to shoot out a radius here. And those are both 25 meters. And by symmetry, this angle here, this one right here, is half of the 129 degrees, which is to 3 sig figs 64.3 degrees. No. Yes. Yes. Yes, because that's perfectly symmetric. So that is 64.3 degrees because it goes through the center. Okay, so now you'll notice that this, of course, is also 64.3. That doesn't make any sense, does it? Because that's 25 and that's 25, and that makes this an isosceles triangle. How is that possible? Interesting. Oh, I see the issue goes further back. The issue is this 129 degrees is not correct. Oh, this is all wrong. This is a tougher problem. Either that or I'm just not seeing the answer. So let's erase those angles because those angles are not correct. And let's try this again. So those are both 25. That part is correct. Now the 129 degrees, I had it in the red, but in reality, the 129 degrees is all of this. That's 129 degrees. That's 129 degrees. So, aha. Okay. Imagine that we have a full circle here of 360 degrees. If you take that 360 and you divide by 7, that makes this here 51.4 degrees. It's 1/7 of the entire circle. So that's 51.4 degrees. And because that's 51.4 degrees, and we know that it's isosceles, if I do 180 minus that and divide by 2, 180 minus that and divide by 2, that makes this here 64.3 degrees, which is the same thing I had earlier. That was the same thing I had earlier by a completely different method. Math is so amazing sometimes. Anywho, so now that means I can use this little triangle that I constructed to find this side right here. And that side right there, we could use the law of sines. I'll say x over sine of 51.4 degrees equals 25 over sine of 64.3 degrees. So sine of that number times 25 divided by sine of that number gives me that x is equal to 21.7 meters. 21.7 meters. So now I have 21.7 meters there, 21.7 meters there, and this angle here is twice 64.3, which I already did, is 129 degrees. All right, which means the area of the playgrounds is 1/2, one side. Sorry, 21.7 is not 25. Does that make sense? $360 divided by 7. Yeah. Yeah. Something's wrong here. This can't be right. This can't be right. 21.7, 21.7 sine of 129 degrees. Let's see what happens. If I square that times sine of that. So this gives me a final answer of 1779, 1780, which I do not think is the correct answer. No, not even close. So let's do what needs to be done, which is we start over and we try to be a little more careful. So I'm going to draw a bigger circle here so I can have an easier time labeling things. So we have 1, 2, 3, 4, 5, 6, 7. 7-sided figure. Okay, labeled as M, N, S, R, Q, P, and O. Okay, we connect M and Q. We connect Q and S. We connect M and S. So we're looking for this area of this triangle right here. I'm going to label it, so I'm going to shade it in. Okay. Okay, so we're looking for this guy right here. Okay, so what do we know? So here's the center. It's off the line. It's over here. This is point T. Okay, so now using a different color, I know that if I go directly to S, this is 25. And if I go directly to Q, that doesn't go to Q. That's 25 because those are both radii. Now, this angle here. Okay, this is not a 1/7 of the 360 degrees. A 1/7 would be one vertex to the next. This is a 2 vertex. So it's 360 over 7 times 2. This is actually 103 degrees. It's 2 vertices worth. 360 over 7 is one vertex. This is 2. Okay, this should clear up everything. So 103 degrees. If I do 180 minus that and divide that by 2, that means this is 38.6 degrees, 38.6 degrees. Okay, which means to find this side right here, we just do, if we call it X, X over sine of 103 degrees is equal to 25 over sine of 38.6 degrees. So sine of that times 25 divided by sine of that gives me that x is equal to 39.1 meters. That makes so much more sense. 39.1 meters. Okay, so now we have two sides, because this is also 39.1 meters. We have two sides of the big triangle, and this angle here by symmetry is twice 38.5 degrees. This is 77.1 degrees. So the area of the playground is 1/2 39.1 squared sine of 77.1 degrees. Sine of 77.1 degrees times 39.1 squared times 1/2. This gives me an area of the playground of 745 meters. Meanwhile, the area of the circle, again, is pi radius squared. 625 times pi is 1963 meters. And if I subtract 1963 minus that, this gives me an area of the flowers, which is 1,200 3 sig figs. So 1,220 square meters. This should be meters squared for all of them. So that's my answer, and I'm sticking to it. A little tricky. Not tricky. I didn't see. Well, I made a mistake. That's what it comes down to. I made a mistake. But this should be a lesson, or could be a lesson, that when you're solving a problem and it's not working, something is not right, you're not getting the right answer, or something does not seem right, sometimes instead of just trying to patch it up, you go back to the drawing board and you just start over, clean slate, make a bigger picture, make a neater picture, try to label things better. And quite often, things have a way of working themselves out. So in this case, that's exactly what happened. Okay, so now let's continue. And the second half of section 2.2, and we're going to have two more formulas. And the first is the area of a sector. A sector is essentially a slice of pizza. Okay, this is a sector of a circle, and this formula is in the formula book. I saw it a few seconds ago as I was flipping through it. Yep, area of a sector is right here. And without looking at the formula, because you don't want to have to rely on it if you don't need to, notice that there's going to be some angle. This here is going to be some angle theta. And we know that the area of a whole circle is pi r squared. Well, we're not using the whole circle. We're using a fraction of the whole circle. And what is that fraction? It's the angle divided by 360 degrees. If the angle is, for example, 180 degrees, it's half of a circle. It's 180 over 360. If it's 90 degrees, it's a quarter of a circle, 90 over 360. In general, it's just pi r squared, the area of a whole circle, times angle over 360 degrees. And that's the formula for the area of a sector. So let's do some examples. Here we have a circle, and it says a crop sprinkler. A crop sprinkler irrigates a circle with a radius of 5 meters. So here's a radius of 5 meters. And then it actually draws a little sector. If you think of a pizza slice, it's a pretty big pizza slice. A, B, C. And we would like the area of the sector BAC with radius 5 meters and central angle 120 degrees. No problem. You just told me how to find it. It's pi radius squared times my angle divided by 360 degrees. No problem. 120 over 360 is a third. 5 squared is 25. So 75 pi over 3 gives me an area to 3 sig figs of 26.2. And we are in meters, so square meters. Next example. The area of a sector. So they draw a picture for me. And they give me a sector. Here's A, here's B, and here's C. So they give me that the area of the sector is equal to 30 square centimeters with a radius of 13 centimeters. And they say find x, the size of the central angle. No problem. The area is pi radius squared times my unknown angle over 360 degrees. It's just a matter of then solving for x. 30 divided by pi divided by 169, which is what 13 squared is, times 360, tells me that x is equal to well, what they have here is not what I have, so I'll just do the math again quickly. Oh, no wonder I didn't read the question correct. 30 pi centimeters squared. So 30 pi centimeters squared. Well, in that case, the pi's just cancel. So I have 30 divided by 169 times 360. And now I do have what they have, which is 63.9 degrees. And then we have the next example. Again, we have a circle. And we have a thing. But now we're actually cutting off a portion of the sector. And they tell us that it's 4 centimeters with a 75-degree central angle. And they want the area of the segment enclosed by the chord AB and the arc AB. So how do I find the area of that? We don't have a formula for that, do we? But we can use a little trick. If you want to find the area of that, what we can do is find the area of the entire sector, subtract off the area of the triangular part of the sector, and then you're left with the area of the tip of the sector. Pretty sure that has a name. I forgot what it's called though. Whatever. So, right, if you take the whole thing and then you remove that part, you're left with the part that we're looking for. So we need the formula for the area of the sector, no problem. It's pi radius, which is 4 squared, times central angle over 360 degrees, minus the formula for the area of the triangle, no problem, 1/2, side 1, side 2, sine of central angle. And now it's just a matter of taking out your calculator. Well, let's see, can we simplify it all here first? Well, the only thing we can do is, pull out a 16, but who cares? So 16, that's 4 squared times pi times 75 divided by 360. So I get 10.5, and then 8 sine 75 degrees gives me 7.73. And then when I subtract, using all decimals, of course, I get 2.74 square centimeters. And that takes us to exercise 2D. Exercise 2D. Question number 1. 3 parts. Determine the areas of the sectors with radius and angle, central angle given below. So here's A. Radius 6 centimeters, central angle 70 degrees. Pause. Solve. Area is pi r squared, pi times 36 squared, which is 36, times 70 over 360. This gives me 22.0 square centimeters. B, r equals 3 centimeters, and central angle equals 49 degrees. Pause. Same thing, pi times 9, which is 3 squared, times 49 over 360, gives me 3.85 square centimeters. C, r equals 10.5 centimeters, central angle equals 122 degrees. Pause, solve. Pi times 10.5 squared times 122 divided by 360. I get area is 117 square centimeters. Question 1. Question 2. Side part A. A sector with central angle 140 degrees. Nope. Central angle 140 degrees and radius 9 centimeters is cut from a wooden circle. Find the area of the sector. Pause, whatever. Pi times 81 times 140 over 360. 99.0 square centimeters. B. A sector with radius 10 centimeters and central angle x degrees has an area of 48 pi square centimeters. Find the angle of x degrees. Find the size of the angle x degrees. Well, again, that's a typo. Find the size of the angle x is what they meant. Pause, do your thing. So 48 pi equals pi times 10 squared, which is 100, times the currently unknown x over 360. The pi's cancel. 48 divided by 100, get that, multiplied by 360, and we get x equals to 3 sig figs, 173 centimeters. Oh, part C. A sector. So it's another circle with radius x centimeters. So x and central angle 50 degrees has an area 8 pi square centimeters. Find the length of the radius x. Pause, yeah. Okay, so 8 pi is equal to pi x squared 50 over 360. Pi's cancel, zeros cancel. 8 times 36 divided by 5. And then we square root that. X has to be positive because it's a physical length. So x equals to 3 sig figs, 7.59. And it's a length, so centimeters. Question number 3. Determine the area of the shaded region. So here's a circle. And here's a 90-degree angle. And we cut across there. And the shaded region is that part right there. And there's two parts. There's A, where the radius is 8 centimeters. And there's B, where the radius is 12 centimeters. So what I want you to do here when you solve this is solve for an algebraic answer where the radius is just r, get a formula, and then apply it to part A and part B. Rather than doing it the same work essentially twice, do the work once, and then plug in A and B at the end. So go ahead and do that, please. Pause. And then hopefully you're back now. So let's get to it. So first, the area of the sector, the area of the entire sector is pi r squared times 90 over 360. In other words, it's pi r squared over 4. Now this isn't really a shock, or shouldn't be, because it's a quarter of a circle. So that's very, very straightforward. Now, what's the area of the triangle? Well, the triangle, let's fix that. The triangle is a right triangle. So it's just 1/2 base, which is r, because it's also a radius, squared. So just r squared over 2, or 2r squared over 4. That seems to complicate things, but the reason I did that is because we're going to subtract these off to get the area of the tip, which is therefore going to be r squared over 4 times pi minus 2. R squared over 4 is in both, so pi minus 2. So for part A, if I plug in 8, so 64 over 4 times parentheses, pi minus 2 gives me 18.3 square centimeters. And B, where I just do 12 squared, which is 144 over 4, times pi minus 2, gives me an area of 41.1 square centimeters. A lot faster than doing the same work twice. Let's just do it once and apply it twice. Question 4. 2 questions to go. We have a circle, and we have a sector, 4 centimeters, 4 centimeters, 55 degrees, cut off here, and the problem is shading here. So let's see what they want. Find the area of the segment enclosed by the chord and the arc. So they want the shaded region. Go ahead and do it. This should be very quick because we did it a few times. We want the area of the whole sector minus the area of the triangle. The area of the whole sector is pi 4 squared 55 over 360. Area of the triangle is 1/2 4 squared sine of 55 degrees. And then it's just a matter of evaluating. So 16 pi times 55 over 360, so that's 7.68. And then 8 sine 55 is 6.55. And when we subtract, we get 1.13 square centimeters. And then now we have question 5. Ooh, and we always know that the last question is the one that is the tough one. So I'm going to be a little more careful this time. I'm going to make a nice size circle here. And it's a hexagon. 1, 2, 3, 4, 5, 6. And they want the outside. I know it's not perfect, but hopefully it gets the job done. Okay, so we got that region there. It says a landscaper builds a regular hexagonal patio in a circular garden. The area not covered by the patio will be covered in grass. The radius, so we go to the edge, is 1.5 meters. Find the area covered by grass. In other words, we want the shaded region. So again, if you imagine a full circle here, we know this part here is going to be 60 degrees because there's 6 congruent triangles. 360 divided by 6 is 60. And that's really all we need. So the area of the whole sector is pi 1.5 squared 60 over 360. The area of the triangle, and this is just one piece, by the way, is 1/2 1.5 squared sine 60 degrees. So when I subtract these, that gives me one of the 6 yellow shaded regions. And then I just multiply by 6 to get the total. So pi times 1.5 squared times 60 over 360. So I get 1.18 minus 1.5 squared, which is 2.25 divided by 2 times sine of 60 degrees, which is 0.974. When I subtract them, this gives me 0.204. And then if I multiply by 6, I go, therefore, the area of the grass is 1.22 square meters. And that takes us to the end of 2.2. So I will see you shortly for 2.3. Bye.